So we have been looking at a very special continuum medium, which is the simplest possible solid, and that is the linear elastic isotropic solid, right? And we discussed how it is this special linear elastic isotropic solid that's the one that needs only two elastic constants or two material parameters to define define its mechanical response completely, right? So we saw that using these two using these two material parameters, which in this case, in this version of its constitutive material response, या constitutive law, are the Lame's constant, which is mu and lambda. So हमने इसकी derivation actually 2 weeks पहले की थी कि then we can write down very compactly the stress-strain relationship that characterizes this linear elastic isotropic material. ठीक है जी. So ये हो गया था, हमने पहले का किया हुआ था. उसके बाद we also pulled in all our previous knowledge regarding just kinematics and just kinetics. That is, we pulled in that we know how the displacement and strains are related to each other, or we discussed a little bit in more detail that if we are developing this very particular theory of elasticity, that is when we're looking at only small strains or small infinitesimal deformations, then the nice thing about that is that our Lagrangian and Eulerian description become approximately the same thing. So that is कि वो material अपनी vicinity में ही रहता है, deforms just so close to its own original position that we can just assume that the current position is actually the same as its initial reference position. And from that, loads of other things end up becoming simplified. In particular, the material derivative becomes very much simplified. और फिर उसकी वजह से आगे जाके हम और कुछ manipulations करते हुए अपनी kinematics को combine कर सकते हैं with our constitutive law, and finally we can plug those two together into our universal law, मतलब law of nature, law of physics, which is the equation of motion, which came from the balance of linear momentum. Or when we plug that in there, we basically can convert all of those three different sort of relationships into one, combined together to get just one equation in terms of the displacement of the continuum. ठीक है, मतलब ये कि इसी के अंदर हुक्स लॉ है, इसी के अंदर हमारा स्ट्रेस स्ट्रेन दैट इज़ द हुक्स लॉ है, इसी के अंदर हमारी डिस्प्लेसमेंट से किस तरह स्ट्रेन आ रही है वो भी इसी के अंदर है, इसी के अंदर हमारा ये है कि देयर इज़ गोइंग टू बी अ बैलेंस ऑफ लिनियर मोमेंटम, दैट इज़ हमारी इक्वेशन ऑफ मोशन इज़ राइट इन हियर, and so on. So that is, we've combined all of that up so that we can get just one differential equation that perhaps then we can solve for various different problems. So now the thing is, it looks pretty complicated, but as I said, we know what's in here. Okay, we know how it came about, or if you think of it just that way, then it's not really, we have no concern, at least personally me, I have no concern कि अच्छा जी ये index notation थोड़ी complicated हो रही है, so what, we know how to deal with that, we know what it means physically, and that's the most important thing. Right? So this is a second order differential equation, second order being that there are differentials up till a power of 2 in the equation. So this is something that we just can solve using various maths techniques. So this is what we discussed last time. or okay, we discussed how this is actually known as the Navier-Lames equations because those two together did some work to come up with this. और फिर हमने in detail इसके बारे में बात की थी कि there are different boundary values which describe different problems. So अगर if a specimen is under tension, then that has its own boundary values. या फिर boundary conditions. If a specimen is under bending or torsion or this or that, whatever it may be for the linear elastic isotropic solid, if it has its particular boundary conditions and we are in the small strain regime, we can apply these Navier's equations, Navier-Lames equations and solve it. ठीक है जी. फिर थोड़ा सा और we did discuss as well कि how do we solve these. So there was a little bit of that. I'm just gonna ignore that part for now and jump basically right into this example which I had skipped last time. To solve a case of a given boundary condition for the Navier-Lames equation. So guys, please have your pens and papers out. I'm certainly going to need your help. So this is a second order differential equation, so I'm very likely to make some mistakes in here. So let's see. Now consider that we have a particular problem. अभी हमें नहीं पता कि वो क्या problem है. आपको थोड़ा सा चले मैं recap दे देती हूँ कि I did discuss कि there are various ways to solve the Navier-Lames equation. ठीक है इस चीज़ को. और दो मेन तरीके हैं. एक तो है ना numerical तरीके से. Numerical means कि where you are using some sort of approximations and some iterative solving method to come to an approximate solution. And then the other way is to find an analytical solution in which you find a true solution. Lekin with that analytical solution could also be an approximate one, या फिर it could be a क्या कहते हैं उसको, I forgot the name, was a exact solution. Yeah, so it could either be an exact or a true solution. So within the analytical ones, I discussed that there are many different solution methods. हमारे कोर्स हम इस सॉल्यूशंस के ऊपर नहीं फोकस करेंगे, लेकिन हम सिर्फ कुछ प्रॉब्लम्स करना चाहते हैं जस्ट टू सी कि हम जो कुछ करते आ रहे हैं वो एंड में जाके क्या उसका एंड रिजल्ट होना है. So that's why in this we had talked that there are some ways in which, for example, there's something called the inverse method, जिसमें आपने पहले से ही assume किया होता है कि क्या displacement strain stress field होगी already, और फिर हम देखते हैं कि अच्छा does it fulfill the Navier's equations. So we sort of working, that's why it's known as the inverse method. We're working backwards. We already start with a displacement field from which we test whether it fulfills the Navier equations, and then we say कि अच्छा okay, now if it does, now I'm going to think about what possibly could be a physical situation in which we could get a displacement field like that. So abhi that's what I'm going to do. I'm going to use an example of the inverse method, which is that I'm actually already going to start with an assumption of the displacement field already. कि मैं assume करती हूँ कि मेरे पास कोई ऐसी कुछ situation हो कभी जिसमें I only have my U1 component that exists, that is non-zero, or even more specifically, this U1 actually only depends on the X1 component. ठीक है जी. So that's why this is what this thing right here is representing, that U1 is a function of X1 in time, that's it, or U2 and U3 are 0. So now what we want to do is we want to see ke, so let's just read through it. So given this displacement field, obtain the equation that must be satisfied by U1 so that it is a possible motion for an isotropic linearly elastic solid in the absence of body forces. Perfect. So we know that possible motion, yeah, possible behavior of an isotropic linear elastic solid is represented by the Navier's equations. The tensor notation, the index notation. So all we need to do is make sure that u1 satisfies the Navier-Lames equation. So इसके अंदर हमें substitute कर देना है. So let's try it out. Okay, so first of all, what I'm going to do is I'm going to start from the right hand side, just to notice that this is, sorry guys, a question? No question? Okay. Is to notice कि ये हम पहले भी डिस्कस कर चुके हैं कि ये Navier's equation जो है, Navier-Lames equation, ये एक वेक्टर इक्वेशन है. देखिए ये u डबल डॉट है इन द राइट हैंड साइड. u डबल डॉट इज द एक्सेलरेशन ऑफ द मटेरियल पार्टिकल. सो बेसिकली बाय कंसिस्टेंसी ऑफ डिमेंशंस, मतलब ये कि अगर ये राइट हैंड साइड एक वेक्टर है तो ये लेफ्ट हैंड साइड पे जो कुछ भी है इसको जब हम सॉल्व करें तो हमारे पास भी एक वेक्टर ही आना चाहिए. ठीक. So my point being कि within this, या फिर ये now looking at the tensor, I can see कि actually there are 3 scalar equations within this one vector equation. This I index can be 1, 2 and 3, representing the 3 components of the acceleration. So already starting from this right hand side, if I look at the u double dot, I can see कि मेरे पास तो सिर्फ है ही u1. तो clearly I know then from these given boundary conditions then that u2 double dot, u3 double dot are going to be 0. So the only solution जो हमारे लिए solve करने के लिए रह गई है, that's actually to figure out कि ये rho u1 double dot क्या है. Right? मतलब ये कि इस vector equation की पहली term, the first term in it, what is that? That's the one that is non-zero and that's the only one that's then of interest to us, basically. तो मतलब ये कि इसकी जो term होगी वो हमें solve करनी है. तो let me write that down. That means, sorry, my touchpad is lagging behind a little bit. So that means now mu u1 comma jj plus mu plus lambda uj comma j 1, and then the body force terms, but there are no body forces, so that one also disappears. That's nice. That makes my life a bit easier. So ek aur is gone. So now let's expand this out. अब वही बात है. The nice thing is वही बात है. इसको ना थोड़ा सा, in my opinion, sometimes you have to separate out कि we think about the thing physically. उसके बाद जब एक क्रेजी किस्म की इंडेक्स नोटेशन की एक्सप्रेशन आ जाए तो बस फिर उसको अंधाधुन इंडेक्स नोटेशन की चीज़ें यूज़ करके सॉल्व करना है, एंड देन वी कैन फॉरगेट अबाउट द फिजिक्स फॉर जस्ट अ लिटिल बिट. ओके, सो व्हाट्स हैपनिंग हियर, देयर इज़ 1 कॉमा जे जे, तो ये क्या हो जाएगा, दिस वुड बी म्यू इनटू जे जे इज़ द dummy index. Whew. So what does this become? Anybody who needs some practice and who would like to try it out before I just solve it, would someone like to tell me कि ये वाली term क्या हो जाएगी, इधर अंदर क्या है when I expand it out?
मैम समेशन होना चाहिए 3 terms का, 1 1 2 2 और 3 3.
1 1 2 2 और 3 3 बिल्कुल ठीक, लेकिन इधर 1 1 when you say which one, what do you mean? मुझे एग्जैक्ट बता दें क्या लिखूं.
मैम मतलब कॉमा 1 1
u1 कॉमा 1 1 फिर
u1 कॉमा 2 2.
बिल्कुल ठीक, एक्सेलेंट. And then finally,
Z1
very good, Ashen. Yes, exactly right. J is the dummy index. So उसी के ऊपर we go from 1 to 3, loop and add them all up. Perfect. 1 वो उधर ही रहेगा because we're looking at the I is equals to 1 term. Perfect. Plus then the next one, mu plus lambda. And similarly for here, now J is the dummy index again. And this time around, or again, I'll give you a few seconds, you guys, to do it yourselves, like everybody practices. And then I'll just do it myself here. Okay guys, I hope आप लोगों ने लिख लिया है. So it is this thing right here, u1 comma 1 1 plus u2 comma 2 1 plus u3 comma 3 1, because it's just the j's that loop and add over. Perfect. So अब हम उन कॉमर्स को ज़रा एक्सपैंड आउट कर लेते हैं ताकि हमारी ज़िंदगी आसान हो जाए कि वो चीज़ें हैं क्या, क्योंकि हम उन्हें सॉल्व कर सकते हैं. सो फर्स्ट ऑफ ऑल, ठीक है, सो दिस इज़, मैं एक दो लिखती हूँ, उसी से हमें समझ आनी शुरू हो जाएगी. ये u1 कॉमा 1 1 मीन्स कि इट्स द डेल, इट्स दो के लिहाज से हो रहा है. सो इट्स द डबल डेरिवेटिव ऑफ u1 with respect to just the one x. So with respect to del x1 square 2 plus again वही u1 का डेरिवेटिव दो दफ़ा, so that is del 2 u1 with respect to, now this time it's del x2 two times, so it's a square, plus similarly del squared u1 del x3 squared. इसी तरह for here mu plus lambda, and then here I have u1 का double derivative, so it's del 2 u1 with respect to, again it's just x1 का 2 times derivative, whereas this term right here is a little bit more interesting. It's the u2 का derivative twice with respect to x2 and x1, so that's del x2 del x1 plus the last one del 2 u3 with respect to del x3 del x1. Dekhein what a long way we've come, okay, from looking at these very complicated looking, yeah, at least complicated looking, वही मैं कह रही हूँ, हम सबको तो पता है कि physically what is in there and it's not really that complicated, but it just looks like it, to actually expanding these things out into making them look even more complicated, but just doing them like it's no big deal, right? Or अब of course we can simplify it very easily even further to notice कि we know कि u2 or u3 are 0, so clearly ये दोनों तो बिल्कुल ही they don't exist at all, so they are 0. Then next, let's also notice कि does u1 exist as a function of x2 or x3? No, it does not. It's just a function of x1. So this u1 with differentiated with respect to is also 0, and u1 differentiated with respect to x3 is also 0. So the only thing that we are ending up getting is simplifying all of this is, I guess, lambda plus 2 mu del 2 u1 del x1 squared. Or इसको indeed we can write the left hand side also as a either if you want to use the partial derivative, या फिर we could use, we remember that the dots are actually the material derivative, it's d by dt. लेकिन we know कि हम एक infinitesimal ये Navier-Lammers equation is for the theory of infinitesimal elasticity. So in that case, this is actually equal to del by del t as well. So this becomes just del 2 of u1 but with respect to time. So we have got our equation for u1. So u1 must satisfy this differential equation for it to be a possible displacement, right? For a possible displacement for a linear elastic isotropic solid, given कि u2 और u3 0 हैं और u1 is only a function of x1. ठीक, इसी चीज़ को आमतौर पे लोग और ज़्यादा सिंप्लीफाई करके लिखते हैं टू राइट इट डाउन एज del 2 u1 with respect to del 2 t2 is equal to actually combine this lambda plus 2 mu and this rho into one constant. Perhaps let me think of some letter. चलें A कर देती हूँ मैं इस वक्त, even though A doesn't look that nice. Most of the time it's like a fancy Greek letter or something. या फिर even चलें I'll discuss what this equation is increasingly looking similar to. So this is the equation that u1 must satisfy. Now I don't know about you guys, but this is actually a familiar looking expression which pops up all over engineering. So for example, this is the equation of similar to, at least similar looking in form, okay, double time derivative and double spatial derivative of diffusion. It's also similar looking to the equation of wave propagation. Or in particular, if we just talk about, चलें अभी हम बाद थोड़ी सी, just give me a few moments and I'll start discussing wave propagation. GSN.
Sorry, it's Amir here. मैम ये जो भी आपने एक बताया था हमें कि टाइम डेरिवेटिव हम लोग ले रहे हैं स्पेशल एंड मटेरियल.
Yes.
I don't get the difference between the time derivative in both of these spatial and material derivatives. As in, aren't they the same? अगर हम लोग x small x and capital X के बीच में तो चलें difference था. But when it comes to time, how are both of these different? If it's not in interface, a small problem.
Great point.
I can't really
Great point. Sorry, just to point out, आमतौर पे when we represent the partial derivative, we use that one to represent it with some particular कि उस पर लिखना हमें ज़रूरी है, because this partial derivative is like a maths function, जिसका मतलब है कि partial derivative of time with respect to what other keeping what other variables constant. So इस पे हमें explicitly state करना होता है कि is it a small x which is being kept constant or is it a capital X which is being kept constant. Alright, so in this case what I forgot to say that when I'm saying the partial derivative, I just mean that it does not matter if it's the small x या फिर it is the capital X in this case, whereas the big D by dt, this thing, this one actually explicitly means that it's the capital Xi which is being fixed.
Okay.
ठीक. So whenever we use the capital D, उसका एक समझ लें कि उसका एक specific बिल्कुल मतलब है कि it must be the particle which is being fixed. It's the capital X which is being fixed. Whereas when it's this partial derivative being written out, that could mean anything. That could mean that it's either the small x or the capital X which is being kept constant. So we have to be a bit more explicit. Okay.
Okay.
So the only nice thing for our theory of infinitesimal elasticity is that for us now it doesn't matter, because for us now, because वो हमने discuss किया था ना कि capital X और small x की distinction ख़त्म हो जाती है. They are approximately the same. Then that's why I forgot to write down कि अच्छा ये वाला या ये वाला, because they're now the same thing. So that's why it's just a bit, मेरा मतलब ये है कि why isn't this a bit nice? This is a bit nicer because ये partial derivative तो हम सब लोग पता नहीं कब से देख रहे हैं, right? Whereas this capital D, we only got introduced to it and there will be fewer people familiar with it. Whereas this is a slightly more general applicability. So by making the small strain assumption, we are making it more accessible for a larger audience, so to speak, even people who are not familiar with material derivatives and whatnot, and like the precise continuum definition.
Okay, all right, thank you.
Okay, so yes, so this was just an example of the inverse method, which is what I meant कि हमने एक already assume की थी form of the displacement field, and then we saw कि for it to fulfill the Navier-Lames equation, we need a condition on U1 कि U1 की अब अगर हम कोई further solve करें ना अब now I know, and I'm sorry for this, कि this starts to go into again other courses territories and we get little bit stuck क्योंकि हम वो सब कुछ नहीं cover कर सकते. Now, of course, I think कि आप लोगों ने undergrad में भी, or even now, I hope कि in your maths course, you may be looking at solving partial differential equations, right? So this is like this is a very specific second order partial differential equation जिसकी कुछ solutions की specific forms exist करती हैं. ठीक है, अभी हम देखेंगे वो क्या हैं, हम we are not going to discuss कि how do we find them and what not, but my point is कि we are putting a limit कि if there is a displacement field like so, that is कि उसका सिर्फ u1 component है और u1 component सिर्फ x1 पे depend करेगा और ये बाकी वाले ज़ीरो हैं, तो in order for it to be a possible displacement field for a linear elastic isotropic solid, then it must be fulfilling this differential equation. तो उससे हमें आगे कुछ पता चल जाएगा अच्छा कि only these forms of solutions are possible for it, not other ones, and so on. And then we can think about okay, so if only these forms are possible, what does it represent physically? Okay? So that's exactly what we are gonna jump into. I've got 2 minutes, so I might as well just introduce what forms of solutions these equations can actually take. Oh, excuse me. Let me keep these for now. So it turns out a solution of this form, where I have a u1 as a sinusoidal function in terms of x1 and time, just x1 and time, और फिर वही कि u2 is 0, u3 is 0. This equation, this displacement field actually does fulfill, if I could open my other one. Did I close it? No, I did not. If this one satisfies the one that we had just derived, which is that del 2 u1 del t2 squared is equals to वो जो a मैंने लिखा हुआ था some constant which was actually lambda plus 2 mu divided by rho का del 2 u1 with respect to x1. Or we can test it. अभी हम देखते हैं, अभी just give me a few minutes. We will see कि does this fulfill this equation or not. And my point basically is कि वही मैं आपको कह रही थी कि हमने एक inverse method वाला तरीका शुरू किया हुआ है, which is कि हमने already assume किया था कि हम सिर्फ देख ही एक particular type of displacement field को रहे हैं और फिर हमने Navier's equation use करके we saw कि then that displacement field must be fulfilling this differential equation. So let's just see what are the solutions, what are possible solutions to this. So one possible solution is a sine function like so. Okay? And as I said, I had no idea beforehand, before starting the problem, what could this mean physically, As we discussed in our last lecture, this inverse method is the approach that mathematicians tend to use. That you just start off with the displacement field on its own, and then when we start to solve it, and we got, okay, it must satisfy this. And then I realized, okay, there are a set of equations which do, such as the sinusoidal function. Then I can think about, okay, right, now I have a very particular displacement field. What does this represent physically? Or here I'm just gonna pause for namaz and then we'll start off again. Okay, what exactly is this thing? Physically, ye kya cheez hai? Actually, the heading just tells you right here. These are waves going through the linear elastic isotropic solid, but we'll come back and discuss these in a bit more detail. So this is where we were, which is we had assumed a form of the displacement field, and then we saw for it to satisfy the Navier-Lames equation, it comes down to it satisfying actually this differential equation, which is for its u1 component in terms of the x1 component. And then this differential equation is actually, as I was saying, it is something which is a bit more familiar. This is something which has solutions which we already know exist, such as the sine function that I've shown you guys right here. So as we'll see shortly, it's not just the sine function, it's even other periodic functions such as the cos function, or even a superposition of these trigonometric functions which would be able to satisfy this differential equation. But we'll discuss that in just a bit. So abhi pehle, let's keep it a bit simple, and let me just tell you that this equation satisfies this this equation. Chale, this equation satisfies this equation. Wow. Okay. Okay. So let's just discuss what this exactly is. So what's happening here? We have the u1 component, and that's actually a function of some constant alpha. So this is a constant alpha. And then sine 2 pi divided by L, again some constant L, x1 minus CLT. Abhi, I know that there seems to be a lot that has come up all of a sudden, this alpha, L and CL. But just the thing to note about these guys is that they're constants. We'll discuss what those are in just a little bit. Abhi, so just focus on u1 is a function of x1 and time, both being within the argument of a sine function. So what happens is that u1 u1 is a function of x1 and time. So let's see, given this displacement field, what happens if I actually draw these out. Let's say first u1 as a function of time for a fixed x1. Maybe मैं किसी एक part, remember now x small and capital X's are the same. So maybe what I'm doing is I'm fixing myself to a particle. Let's say x1 is equals to 10 पे मैंने अपने आप को, that's my focus, that's my point of interest. So I'm looking at that. This is just an example, okay? So what happens to u1 at that position? We see that as a function of time, it's actually a sine function. मतलब ये कि अब अगर ये भी constant हो जाए तो still what it ends up looking like is a sine function. Sorry for the changing frequency and whatnot, that should not be changing, it's a fixed frequency, it's a fixed frequency. But in any case, I'm just trying to point out okay, at that particle's position, that particle is oscillating about its original, let's say, wasn't a constant being added. I drew it incorrectly. that particle is oscillating about its mean position, about its undeformed position, whatever you want to call it, about its zero position where there is no displacement. So this is something jo I think we all are familiar with and is referred to some sort of a wave motion that a particle might be undergoing, right? It's oscillating at its mean position. So particles पहले ऐसे जाता है अपनी mean position पे u1 है, right? By the way, u1 मतलब ये कि x1 direction का let me also draw in the components. So this is the x1 direction, the other x2 direction perhaps, and then the x3 direction, etc. So this particle is vibrating, yeah, it is oscillating in this u1 direction like so. Aage piche, that's all it's doing. So to and fro harmonic oscillations. Perfect. So the particle itself is oscillating about its position. But what if I actually fix myself in time and I look at how the displacement is changing across space? Matlab ye, how the displacement is changing across particles. So even then, if I do that, for example, I'm looking at a snapshot at say, let's say t is equals to 1 second, and then I plot my u1 against x1. मतलब ये कि for example, let's consider कि it was some sort of a infinitesimal medium. कोई एक material है, actual solid, something like this, some sort of a shape like this. तो उसके अंदर then what I'm saying is कि मैं x1 across देख रही हूँ कि ये सारे particles जो x1 different positions पे lie कर रहे हैं, वो एक time पे what were their displacements. Even that turns out to be as you can see, if I keep the time a constant, that turns out to be a sinusoidal function. That is, even for that, what's happening is कि वो particles यहाँ वाला particle अभी currently maybe इतनी displacement किया हुआ है, whereas another particle is actually not displacing at all, whereas a particle further down is displacing in the opposite direction. That is to say कि वही harmonic oscillation जो है ना, that is actually traveling about, that it's a wave that's traveling through the medium. And that's what I was trying to imply कि this solution of that, वो जो हमने अभी differential equation देखी थी, which we've been considering, this solution actually represents a wave traveling through the medium. Okay? In fact, because there is no boundary condition saying कि वो इस time से पहले नहीं है, इस time के बाद है, and so on and so forth, this is representing an infinite train. मतलब वो waves, they are just going through the medium throughout. ठीक? And then what I said was that there are these extra teensy bits, constants right here and there. So alpha, L and CL, these actually represent something. So alpha here represents the amplitude of the oscillations. This alpha. L actually represents L represents the wavelength of the waves. ठीक है जी कि ये अगर मैं u1 against x1 देख रही हूँ, so what is the distance between two particles at opposite ends of the entire wave basically. Whereas this CL जो है, this represents actually I believe it represents the speed with which the wave is traveling through the medium. मतलब ये it represents the speed एक किस्म की with which कि ये वाला peak displacement जो है वो अभी यहाँ है और अब अगली वाली कहाँ होगी in the medium and so on. So this is the wave speed. So all that I'm trying to say is that we didn't really know okay we'd end up getting this solution but we started with this randomly chosen displacement field, and then it turned out that okay, if we choose, if we are imposing कि this is for a linear elastic isotropic solid, तो फिर उसकी सिर्फ कुछ particular solutions ही हैं, और वो solutions कुछ ऐसी चीज़ें हैं जो geometrically exist करती हैं, जो physically exist करती हैं, such as this displacement field that I've just shown you right here, which is the case for a particular type of wave motion. So please just note that this is what this displacement field is representing. इसको हम अभी physically discuss कर रहे थे, लेकिन अभी let's go back to the sort of the linear elasticity part of it, which is the one that हम लोग जिस पे focus कर रहे हैं, less so on the particular problem. So there is a few more things which I probably should state for this particular wave motion, which is that in this case, as I had said, that the displacements are in the x1 direction, मतलब कि u1 है खाली और वो x1 की direction में है, ठीक है? नहीं, sorry, there is only u1, sorry, I've got that wrong. u1 is displacement in the x1 direction. That's why I meant that there's only displacement in this direction. See, u2 is 0, इसलिए उनकी कोई upwards oscillation नहीं है, उनकी सिर्फ oscillation है ही उस direction में in which direction the wave is traveling, and that is why this type of a wave is actually also, it is known as a longitudinal wave. Now this leads us back to like our school days. I think we all know an example of a longitudinal wave, which are sound waves. So when a sound wave is traveling through a linear elastic isotropic medium, they will fulfill this equation right here, and automatically, because ये तो solution ही हमारी Navier-Lames equation की थी, that would mean कि हमारी physical laws, हमारे constitutive law, सब कुछ satisfy हो रहा होगा. So we're all good, right? अभी लेकिन I just want to show you guys even yes, so let's try to see कि imagine कि हमने उल्टी direction में ना शुरू किया होता, that is हमें पहले से ये ना पता होता कि u1 is actually x1 और t का function, और बल्कि instead इस दफ़ा let's have this particular displacement in mind, or let's try to apply our sort of continuum mechanics principles to this displacement field. मतलब ये कि अभी just a while ago I'd actually used the Navier-Lames equations, ठीक? मतलब ये कि I'd assumed this and then applied the Navier-Lames equation. But for now, let me jump to the other way, which was कि Navier-Lames के अंदर क्या चीज़ें हैं और वो मुझे इन पे apply करने दें एक एक करके. Just to show you guys कि they are completely equivalent. So either we can take this one approach, either we directly apply Navier-Lames equation, or we actually apply in sequence the strain displacement equation, the stress strain equation, then the equations of motion. ठीक? वही चीज़ें which make up the Navier-Lames equations, just to see what happens this time around. Okay, so if I go via the longer route, it's not necessarily longer, but just the step-by-step route which makes up the Navier's equation, then what I'm going to have to do is, first of all, is given displacement field, so I'm going to have to start by finding my strains, of course. Or we all know what the strains are. Actually, I probably would be a good idea. Sorry, I have all of them written out here. So it's either this is one approach, ये तीनों अलग-अलग, या फिर we have our Navier-Lames equation which combines all of them together. So abhi we're using these three. So of course the first step is that we take the displacement field and find our strains from it. Now the thing is, notice that let me just write down our displacement equation. It is alpha sine of 2 pi divided by L is a function of x1 minus the wave velocity times time. And u2 and u3 are 0. This is what we have. So just looking at this, I hope we can all acknowledge that there's only u1 as a function of x1. तो अगर मैं अपना strain tensor निकालूँ ना, जो जिसकी अगर हमें याद ना हो किसी को, तो you can always write it out, expand it and see कि वो क्या चीज़ है उसके अंदर. You will see basically that the only non-zero component is going to be the normal strain in the one direction. That is only that strain component which depends on u1 and x1, मतलब which relates u1 and x1, because सिर्फ वही दो हैं जिनकी relationship exist करती है. Everything else is going to be 0, because just write down the strain tensor and stare at it for a little while, ताकि you have an idea of what are each of those individual terms. Okay, so for now, and I'm sorry for just moving on very quickly, लेकिन हम strain को बहुत दफ़ा देख चुके हैं, इसलिए अगर अभी भी किसी को ये बात बहुत sudden jump लग रही है, so I think you still that's a sign that you should write out the strain tensor and stare at it and think about it कि okay, अगर ऐसी displacement होगी तो strain tensor कैसा होगा, या फिर ये term represents what, and so on. Okay, so there's only a normal strain in the one direction, so there's only epsilon 1,1, and of course the epsilon 1,1 is actually just equal to del u1 with respect to del x1. That's what epsilon 1,1 is. Again, if you don't remember, write it out. So I've just written out the differential right here. Don't need to do anything more fancy. Perfect. Now, next, once we've got the strain components, then what I can do is I can use my Hooke's law, this one. So this was 1. Now I can use my Hooke's law, that is my constitutive material behavior for the linear elastic isotropic solid, and find my stresses. अब इसके लिए भी, और I think for this what's required is कि we stare at our Hooke's law for a little while. अच्छा चलें, ये हम सब ने इतना ज़्यादा नहीं किया हुआ, तो I'll do this with you guys. I will stare at the Hooke's law. Let me open that one up. कौन से वाले पार्ट पे हमें चाहिए? I think एक सेकेंड. No, not this one. This one is the जो lambda और उसी के version में है. Yes, either one of these will do. So let me just stare at this to point out कि अगर हमारे पास सिर्फ epsilon 1,1 है, सिर्फ epsilon xx exist करता है, all the other terms are 0, then can someone already spot कि हमारे पास कौन से stresses exist करेंगे? Anyone? Hello. If I only have epsilon xx, yeah, epsilon 1,1, which stresses are going to exist?
Normal stresses only.
The first 3. Excellent. Thank you. It's only the normal stresses that are going to exist, that is, that are going to be non-zero. The shear stresses, remember हमने इस पे भी discuss किया था, there is no normal shear coupling for an isotropic solid. So the shear stresses are just going to be 0 अगर कुछ shear stress है ही नहीं, जो कि that's the case here. So it's only for the normal strains, if I have an epsilon xx, then वो किस चीज़ से multiply हो रहा है? epsilon xx का ये column है. Oops, ये this first column. और फर्स्ट कॉलम में ये 1 2 3 पहली 3 टर्म्स होंगी, दैट्स इट. So that is, I only am gonna have sigma 1 1, sigma 2 2 and sigma 3 3. Baki sari sigma ki terms, the shear stresses are gonna be 0. Or on top of that, maybe it's up to you which one you prefer. Either because you've stared at this for so long, as I said, that you're already familiar कि if I just have epsilon 1 1 तो फिर इनकी क्या values होंगी, या फिर you just apply it, plug it into your written out index notation form of Hooke's law. So the point is कि फिर sigma 1 1, sigma 2 2, sigma 3 3 की exact expressions find कर लेते हैं हम. So sigma 1 1 of course is just going to be 2 mu times epsilon 1 1 plus lambda times the trace, जो कि है ही trace क्या है strain का इस वक्त, just epsilon 1 1. So that is sigma 1 1 is going to be 2 mu plus lambda times epsilon 1 1. Just that. और sigma 2 2 and sigma 3 3 क्या होंगे, वो उनके अपने strain components 0 हैं. They're only arising because of the trace part. They're only arising because of epsilon kk. So that is, for sigma 2 2 and sigma 3 3, what I'm going to get is just lambda times epsilon 1 1. And that's it. The other ones are all 0. And then if I know, so I already know what epsilon 1 1 is, so I can pop that in, I can substitute that. So इसलिए that's all that I've, ये मैंने यही चीज़ उठा के यहाँ सीधा लिख दिया इधर. Okay, again it's perfectly fine अगर हम वही फिर से के इंडेक्स नोटेशन वाली मल्टीप्लिकेशन कर करके फिगर आउट कर रहे हैं, लेकिन दैट कैन टेक अस अ लॉन्ग टाइम समटाइम्स. सो इट्स अ गुड आइडिया. Guys, somebody's mic is unmuted. Any question? No. So it's a good idea. What I was saying was, it's a good idea कि आप सिर्फ इन लोगों की जो expanded expressions है ना, लंबी लंबी पूरी second order dyads की, you look at it for a while and think about what it means कि okay, epsilon 1 1 जो है वो है क्या चीज़. It's a function. It relates u1 differentiated with respect to x1. Okay, so epsilon 1 2 क्या है, and so on and on and on. Similarly for the stress tensor as well, because that then gives you some physical insight into looking at an equation and telling कि okay, इसकी वजह से किस किस्म के strains arise करेंगे या किस किस्म के stresses arise करेंगे. So it can be very useful. Okay, so now that we've got our stresses, then the third step just left is to plug them into our equation of motion. What time is it? Okay, we are coming close to your quiz time. Just a few more minutes, please. So just plug it into our equation of equations of motion. Again, I believe we've just got u1. So the only non-zero component of the acceleration is going to be u1 a1. So उसके अंदर हम substitute कर दें. So ये जो इतना complicated सी चीज़ लग रही है, that is all that's been done. Okay, बस straightforward substitution. So this right here, let me figure this out. This term on the right hand side is our sigma ij comma j. और this term right here, sorry मैंने ये order यूं करके लिख दिया है, is our rho u double dot 1. और प्लीज़ नोट, ये सिग्मा आई जे कॉमा जे जो है वो 1 वाले के लिए that turns into sigma 1j comma j. So the nice thing about that even is कि only sigma 1 1 comes into effect. right? Sigma 1 और फिर वाले sigma 1 2 तो 0 है, sigma 1 3 भी 0 and so on. So it's only sigma 1 1 which is of importance to us, and that differentiated with respect to j, to 1 होगा फिर खाली रह जाएगा. Anyway, so that's what's been done right here. It looks a bit complicated, but it is not. We just have to follow through with solving this and differentiating the displacement twice and comparing these two equations. Then we figured it out. So we've got this sine function which cancels out. What else have we got? We've got 2 pi divided by L squared, that cancels out. We've got alpha which disappears as well. So the only things that we've ended up getting remaining are CL squared rho and this lambda plus 2 mu. So simplifying this, we can find कि what exactly this phase velocity जो मैं आपको कही थी ना कि वो wave की equation के अंदर जो velocity थी उसकी, we can figure out what this phase velocity was or is for our longitudinal wave, and that's going to be actually equal to this lambda plus 2 mu divided by rho half. And if you notice कि this was the same constant that we were getting when हमने directly Navier-Lammez equation use की थी, उसमें we had got this lambda 2 u1 lambda t squared is equals to जो मैंने a लिखा हुआ था, जो a actually यही चीज़ थी, इसका squared था basically. So even अगर हम लोग familiar होते already कि ये तो wave equation होती है, तो हम directly भी कह सकते थे कि this is actually the wave velocity squared. But I was assuming कि हम लोगों को actually ये पता नहीं है कि ये equation एक standard form है. Whereas now we have managed to find the wave equation. Please note the L, the C represents the speed and the L is representing the longitudinal nature of the wave. And as what we're seeing right now is, अच्छा चलें अभी quiz आने लगा है, फिर हम इसकी physical बातें थोड़ी देर में करते हैं कि what the phase velocity is turning out to be a function of.
मैम annotations वाली.
मैंने sorry Yasin.
चलिए मैम कोई बात नहीं, ऐसे सवाल
जी,
तो मैं ये टॉप राइट कॉर्नर के अंदर हमने जो सेकंड इक्वेशन लिखी हुई है उसके अंदर एक सिंबल आता है डेल आई जे का.
Yes.
मैम जब हम लोग इस इक्वेशन को पुट कर रहे थे नॉन जीरो स्ट्रेसेस निकालने के लिए, तो यहाँ पर डेल आई जे कहाँ चला जाता है?
डेल आई जे कहाँ चला जाता है? ओके. Okay, so let me explain. Basically, जो del ij है, you remember when it's equal to 1? When is it equal to 1?
Ma'am, when I equals to j.
Exactly right. So when I is equals to j, only then del ij is equal to 1, right? So all that this del ij does is it tells us कि ये टर्म, ये प्लस लैम्डा एप्सिलॉन के जो है ना, मतलब ये कि लैम्डा ट्रेस जो है, दिस विल ओनली गेट एडेड टू दोज टर्म्स जहाँ पे i इज इक्वल्स टू j, वरना द लैम्डा एंड द ट्रेस दे गेट मल्टीप्लाइड टू 0. So what that means is, if you think about this now, so of course stress is a second order tensor, right? So it is this thing.
आइडेंटिटी मैट्रिक्स होगा ये.
Oh, yes. So ये तो हमें पहले ही पता है. Ronecker delta जो है, it's just the index notation of the identity tensor.
ओके मैम, थैंक यू, क्लैरिफाई हो गया.
हो जाए, ओके, इधर ही ख़त्म होगी बात. चलें ठीक है, लेकिन मैं let me just complete this thought in case किसी और को नहीं clear. The point of the del ij is कि this lambda epsilon k would only, as your colleagues have pointed out, it is only non-zero when I is equals to j. That is, it is only non-zero for these diagonal terms. So only for these is there going to be that plus lambda epsilon k. बाकी ये जो shear वाली terms हैं उनमें it does not come into effect. That's what this delta is doing. ठीक है जी. Okay. So right. So that's been clarified. So let's move on with our discussion of waves going through a linear elastic isotropic solid. So we've looked at it in two ways. One was to just assume a displacement field and pop it into our Navier-Lames equation to find out what it should satisfy. And then फिर मैंने एक और displacement field जो even more specific थी उसको consider किया, which was this sinusoidal displacement field. Sinusoidal, just the u1 being sinusoidal in terms of time and x1. Or we saw that if that is the case, then we are able to actually use our standard procedure of finding the strains, stresses, and then applying the equations of motion to figure out what, let's say, one of these at least constants in the displacement equation turns out to be. So it turns out that our CL constant, which I said कि वो जो expression लिखी हुई है ना, ये as engineers and as physicists and as just even mathematicians, we are familiar that this equation written right here actually looks or is a wave equation. ठीक है जी. Oh, sorry, I forgot the 2 pi divided by L here. So इसको अगर हम try कर रहे हैं कि अच्छा ये wave equation को fulfill करनी है Navier-Lames, so then we are able to figure out कि okay, that means कि this wave speed must be equal to this for this wave to be traveling through the linear elastic isotropic solid. ठीक. अब this might seem pretty trivial to you guys, लेकिन what's happening is कि इससे हमें पता चल रहा है कि वो wave, it can only take a very specific speed depending on what material we have. Look at this, what's inside. It's lambda plus 2 mu divided by the density of the medium of the isotropic solid. मतलब ये कि depending on which linear elastic isotropic solid we have, these material properties are dictating the wave speed. और इसी चीज़ को यूज़ करते हुए ना, there is this entire sort of field where people are able to detect. I think you guys might have heard of non-destructive testing using ultrasonic waves and so whatnot in materials, because if you already know कि क्या speed होनी चाहिए given a isotropic solid, and if there are changes happening within this phase in this wave speed, then you can sort of figure out how much is your medium deviating from your isotropic assumption, and so on. And other things as well you can do. So that's one thing to note here, that if I have a isotropic steel specimen as compared to an isotropic copper specimen, as compared to some other isotropic plastic specimen, let's say, they will all have their own wave velocity. For example, if there's sound traveling through it, it will have its own velocity as speed going through that, and we can figure that out basically. Okay. There are more aspects to this particular type of wave. One that we've already talked about, that because it only has displacement in the u1 direction, only in the x1 direction, sorry, that's why it is known, and it's traveling in that direction as well, that's why it's known as a longitudinal wave. But another important aspect of this wave is that rather than the strain, jo ki strain to we know is the symmetric part of the displacement gradient, if I actually find out the anti-symmetric part, right, anti-symmetric part of the displacement gradient, if you guys recall, we are able to find the infinitesimal rotation tensor that way, that we used to represent by small wij. और इसी से actually is also related to the spin tensor as well of the velocity field, but let's ignore that part for now. But the point is that if you look at that displacement field, which is just a function of x1 and time, we can see that actually its displacement gradient is symmetric. It does not have a skew part. Therefore, it does not have any rotation within it. That's why there is another name for these waves, and they are known as irrotational waves as well. They don't cause any spin in the medium, so to speak. Okay. Nothing fancy here, just उसको नाम देने के लिए फ़र्क तरीके हैं. So these are, as I said, different names for it. So longitudinal waves and irrotational waves are actually the same thing essentially. Perfect. Okay, so what else am I? So the phase velocity depends only on the material properties and not on the wavelength. Yep, yeah, so we saw that. And yes, so any ये भी हमने बात पहले डिस्कस की थी कि any displacement field that satisfies this equation, this should be the u1 component with respect to the x1 component. Any displacement field that satisfies this will actually be an irrotational wave. Or abhi we had just looked at a sinusoidal wave, as I'm saying that even other ones, for example, if I look at a combination of a sinusoidal and a cosine wave added together, we will see that even this satisfies our differential equation right here, this one, and hence are actually examples of longitudinal waves, या फिर of irrotational waves, even though they look more complicated. Okay, so I just want to do one more example for this slightly more complicated wave displacement, and just consider ke, okay, now knowing all that we know about strain, stresses, equation of motion, or the Navier-Lames equations, how can we figure out various things for a given boundary condition, right? So this is a boundary condition, right? We know the displacement field, or I think hame aur bhi kuch problems will be given. So let's just see what we can do with it, what we can figure out. Okay, so consider that we have a material half space. Now what a half space means is ke a part, matlab it's infinite but half infinite, right? It's like is direction mein infinite hai, is direction mein infinite, and so on. But here there's just one boundary. Okay, so that's what a material half space is, that lies to the right of the plane x1 is equals to 0. So this is the point where x1 is equals to 0 और उसके right पे वो lie कर रही है. And now what we're doing is we're considering the displacement field, which is like so, which we've already seen. This is again it's just got it's a sinusoidal and a cosine function added up. और ये added up equations जो हैं वो वही differential equations को easily fulfill कर देती हैं, because differentiation is distributive. So this actually is an irrotational wave. या फिर वही it is a longitudinal wave. What's happening again? u1 is a function of x1 as before, and just time, nothing else. Okay, so we want to, for one set of boundary conditions, determine the constants alpha, beta, and the wavelength L, and the surface fractions on the plane x1 is equals to 0 इस plane के ऊपर, if the applied displacement on the plane x1 is equals to 0 is this. Okay, so given that, let's assume कि हमारे पास कोई ultrasonic probe है which is being attached right here on this plane, और वो probe is causing the displacements within this medium, right? It's causing the wave to travel through it, और वो probe of course इसी plane की displacement को क्या कहते हैं अप्लाई कर रहा है इसी के ऊपर. So the boundary condition is this one right here. Okay, on this plane, this is the displacement that we have. So let's see how what that means for the entire wave equation then. Okay, pens and papers out, guys. Okay, so clearly at this point x1 is equals to 0 or x1 is equals to 0 पे ये displacement है. So what we know then is, और वो भी क्या है, u1 है. So we know u1 at x1 is equals to 0 at any time t is given to be equal to b sine omega t in the e1 direction. तो बस वो यही हो गया ना, that's it. u1 है, इसीलिए मैंने e1 की जगह u1 लिख लिया था. ठीक. Let me explain what I meant कि e1 की जगह u1 लिख लिया. इस चीज़ से मुझे सिर्फ ये पता चल रहा है कि u जो वेक्टर है that is actually equal to b sin omega t e1 में, e2 से 0 है, e3 पे 0 है, right? या फिर in other words saying what I'm saying is कि I can see कि u only has a component in the one direction. That's why I've written कि u1 is equal to this. बस बाकियों को भूल जाएं, u2 u3 जो 0 हैं उनको गोली मारें. That's trivial, right? Okay, so अब u1 अगर ये है तो u1 की तो हमारे पास पहले ही एक्सप्रेशन है. So let's just substitute x1 is equals to 0 to find के u1 क्या होना चाहिए था. We see that becomes alpha sine 2 pi divided by L. x1 0 हो गया है, so minus CLT plus beta cos again 2 pi divided by L. Again x1 is 0, so minus CL by T. Or at this boundary we know that it should be equal to b sine omega t. Or as I said, this is the applied boundary condition, right? तो ये हमारा वो जो probe था उससे determine हो रहा है कि ये amplitude होगा और जो उसकी ये angular velocity है. Okay, so simplifying this further, sine के अंदर minus हो तो वो बाहर आ जाता होता है, whereas cos के अंदर minus हो तो that just becomes it's the same as having a positive. This is something to do with वो जो quadrants नहीं होते A, S, T, C. I believe you guys are familiar with this. So for the cos वो first or fourths में, so it's like a reflection. So it's the same thing if you have a minus angle and you take the cos of it. Whereas for the sine it isn't. It's only positive in the first two quadrants, not in the next two. Right, okay. So coming back here. Now if you want to solve this, clearly on the right hand side there is no cos function. So अगर हमें इसको ट्रू करवाना है, so only साइन वाले ही चीज़ एग्जिस्ट करनी पड़ेगी ना. So that means कि जो बीटा है, this beta is actually equal to 0, so that we just get the sine function. And secondly then further comparing we can see कि alpha तो आ गया then equal to minus b. And finally from the arguments within the sinusoidal function we see that omega is equals to what? 2 pi CL divided by L. और हमने find actually wavelength करनी थी L. So that becomes that L is equals to 2 pi CL divided by omega. And remember CL is a constant. The phase velocity we have now just discovered अभी एक तो 5 मिनट पहले, that's a constant that depends on the material. So this is not going to change.
Ma'am?
हाँ जी.
अल्फा माइनस बीटा के इक्वल है, माइनस बी के इक्वल होना चाहिए.
Thank you so much. Yes, alpha is actually equal to minus b, not this. Thank you, minus b. Yes, thank you. Thank you for pointing that out. Right, so Cl is a constant that depends on the material. So इधर जो डिपेंडेंस फिर आपस में हो रही है वो हो रही है कि डिपेंडिंग कि किस एंगुलर फ्रीक्वेंसी पे हमारा प्रोब वो वेव्स भेज रहा है उससे डिटरमिन होगी कि उन वेव्स की वेवलेंथ क्या है, नथिंग एल्स. उनकी वेलोसिटी को वो कंट्रोल नहीं कर सकता. सो इट जस्ट कंट्रोल्स कि उनकी प्रोफाइल व्हाट इज इट गोइंग टू लुक लाइक, ये वेवलेंथ क्या हो जानी है, दैट्स इट. Right? So we figured out what alpha is, what beta is, and what L is. And then there's the last bit which is still left. Okay, what is the surface traction on this plane? Sure, okay, that's a great point. Okay, we probe which is sending out these waves. What traction is that causing on this boundary? मतलब ये कि उस पर क्या stresses develop होंगे. Perfect. Okay, so for that let's actually figure out. That's something that I'm gonna, मैं भूल गई थी वो वाली equation लिखना. That was just the kinetics part. I forgot to write that down. That used to be, you guys remember on traction, we could find the traction vector on any cut plane, right? So that was sigma transpose multiplied by the normal vector of that plane. Right? So अगर हम पहले sigma find कर लें, or of course we know what plane we're talking about, then we know the normal vector as well, then we can find the traction. Okay, so that's the approach basically that we're gonna have to use. So for sigma, what can I do? I can actually use my displacement to find the strain and then use that strain to find the stress. So let's do that. Excuse me for doing this, but let's read through it because we figured it out what to do, right? So let me use the slides to move things along a little bit. So just last thing to point out ke knowing these beta, alpha and omega, or then I know I've solved this boundary value problem basically, and I know कि u1 की expression क्या हो जाएगी. ये तो सब गायब हो गया, and the only thing I've got left is this alpha, which is minus b sine of L को वैसे ही रहने दें या नहीं, नहीं चले नहीं रहने देते. L is 2 pi CL divided by omega, so 2 pi और 2 pi cancel, and I end up getting left with omega divided by CL multiplied by x1 minus CLT. This is our simplified displacement field, of course with u2 and u3 is equals to 0 for these particular given boundary conditions. ठीक है जी. So the reason why I wanted to write down this u1 explicitly like this, जो simplified है, is ताकि हम अपना strain निकालें. हम अपना strain निकालें और strain से stress निकालें. ठीक. So let's just skip through that part a little bit, or basically just where did it go? Basically just consider directly कि we have, let's assume कि हमने stress निकाल लेंगे, हम figure out कर लेंगे. Again I'd like to point out कि अभी क्योंकि हमने एक example की थी डिटेल में और हमने इस पर बात की थी, इसलिए मैं assume कर रही हूँ कि हम we've got the hang of this, which is कि look at this displacement field. It's u1 in terms of x1 only. That tells me कि only what would exist. Anyone? Which strain component would exist?
E11.
Only epsilon 1, exactly right. Only the normal strain in the one direction, that's it. And if only this strain exists, then only which stresses exist? Sigma 11, sigma 22 and sigma 33, as we just discussed previously. ठीक है, which means कि my expression for this surface traction, remember ये अभी मैंने लिखा था, this can become a little bit easy to point out. This is just going to be sigma 11, sigma 22, sigma 33, 0, 0, 0, and then it is symmetric as well, of course. And this now has to be multiplied by the unit normal. Now remember, अब आ जाते हैं हम अगले वाले part पे ना. So ignoring कि ये है क्या, we will talk about this in a second. Let's get to the new part to find this surface traction. So it's a infinite half plane. Something like this. So only x1 is equals to 0 पे एक boundary है. Remember, the unit normal always points out of the surface. So the unit normal must be this one. And what is this? According to normal convention, this seems to me that it is, अगर हमने मुझे अपना coordinates define करने होते, that would have been x1 to the right, x2 up above, and then x3 coming out. So clearly this unit normal is actually minus 1, 0, 0. है कि नहीं? It's going in the minus x1 direction. So that's telling me that my traction vector that I'm interested in actually turns out to be minus sigma 1, 1, 0, 0. I've just multiplied these two together to get this. So if I find my sigma 1, 1, ये वाला जो हमने पहले किया हुआ है, इसलिए I'm not gonna go into कि किस तरह हम कर रहे हैं, how the detail of it. We saw already, just to point out, कि sigma 1, 1 had turned out to be lambda plus 2 mu epsilon 1, 1, and epsilon 1, 1 is of course just equal to del u1 by del x1. So I know what sigma 1, 1 is, and then the traction vector is just that, the minus of that acting there. So that हमने simplified, हमने find कर लिया. Right? So let's just write that out. As I said, it's just, apologies for the t, this t here is just sigma transpose, yeah. So as we discussed, sigma 1, 1 was lambda plus 2 mu epsilon 1, 1, or epsilon 1, 1 is del u1 by del x1. So just substituting all of this information right in here. Also of course noting that del u1 by del x1 evaluated at x1 is equals to 0, क्योंकि इसी plane पे तो निकाल रहे हैं हम, पूरे उसके लिए थोड़ी निकाल रहे हैं, सिर्फ इस plane के लिए, इस point, इस boundary के लिए निकाल रहे हैं. So when I'm finding del u1 by del x1, I have to have it at x1 is equals to 0 to find it. Right? And then just substituting everything in there, this is our traction vector. Okay. I have a feeling that things are becoming complicated pretty quickly, right? The thing is that it's just that we're starting to see how it may be possible to actually solve real world physical problems or analyze them using all the continuum mechanics that we have learned. Or I intentionally chose the wave problem for one reason, कि apart from the fact कि वो ये sinusoidal function आ कहाँ से रहा है, जो हम नहीं जा रहे उसमें, हमने कहा ही नहीं कि हम वो differential equation को खुद solve ही नहीं कर रहे. After that, it's actually pretty, it's straightforward. Whereas the issue with other boundary value problems such as, मैंने आपको कहा था कि Navier-Lammy's equation, it's applicable for it's applicable for any boundary value problem of a linear elastic isotropic solid. So the issue with all the other ones, so for example bending, ठीक है जी, यहाँ से ये bend हो रहा है इसकी वजह से, इसके ऊपर जो moment लग रही है, या फिर of torsion when something is warping या twisting so to speak. The problem with these, even for uniaxial tension, is कि ये तो खैर actually it's a bit too simple, that's why I did not consider it. The problem is that these are a bit more difficult to solve and to understand कि how the Navier-Lames equation की solution कैसे आ रही है. Whereas for the wave problem, even though that's a little bit more complicated problem physically, it has more meat in it for the analysis that we've considered in continuum mechanics. मतलब ये कि as you've just seen कि हम उसको solve करके, उसको use करके उसकी displacement equation को हम figure out कर सकते हैं जी कि क्या strain होगा कहाँ पर, let's say, या फिर वो strain with time कैसे vary कर रहा है, या फिर कि एक बाउंड्री पे क्या पर्टिकुलर स्ट्रेन है और उस स्ट्रेन से क्या स्ट्रेस डेवलप हो रहा है, एंड सो ऑन. That is, we can apply all the kinematics and the kinetics that we've looked at beforehand in our course so far. कि ट्रैक्शन क्या है एक कट प्लेन के ऊपर, and so on and on, right? So इसलिए I understand कि ये क्या हो गया, एकदम से waves आनी शुरू हो गई हैं. Lekin the idea is that it's not, the physical problem is not the one that's too overly complicated, yet it is a good example of us using all the tools that we have learned in our course so far, right? Using our equations of kinetics and kinematics and what else we have been looking at. Okay, two physical problems, right? So I've actually just managed to do part A. Okay, so I guess it's time basically for part B. Would you guys like to take a break, or should we carry on? If we don't take a break, we will finish by 7:30. If we take a break, then we will probably finish by 7:45 or 7:50.
And continue.
Okay. चलेंगे. So B part को let's see part B. So चलें, हमने कहा no break. मुझे break चाहिए थी, लेकिन चलें, it's okay. Let's do it. So now we have a slightly different set of boundary conditions. ठीक है, plane वही है, लेकिन पहले हमारे पास एक displacement apply हो रही थी on our infinite half medium. Whereas this time around what's happening is determine the constant da 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 and the displacements on this plane x1 is equals to 0 as before if the applied surface traction on the plane is given by this. Matlab ye, you remember we had discussed that there can be boundary conditions of various types. There can either be the displacement boundary conditions or the traction boundary conditions or a mixed boundary condition state. So for in the part A we considered displacement boundary condition. जब इधर वो probe could displacements, it was displacing it and causing the wave motion. Whereas in this part B, instead it is applying a traction. So let's see कि इस दफ़ा क्या होता है. Does that change things up? What happens? Okay, so determine the constants alpha and beta, the wavelength lambda, and the displacements on the plane x1 is equals to 0 if the applied surface traction on the plane x1 is equals to 0 is given by this. Okay, so now we're in business. So अगर ये traction इधर की given है, we've already seen that the traction is actually equal to sigma transpose time n, which n we've discussed is actually equal to -1, 0, 0, because वो x1 तो यूं है ना, उसकी माइनस डायरेक्शन में. So that is, as we had done before, we see that the traction vector actually turns out to be just minus sigma 1, 1, 0, 0. So मतलब ये हुआ, comparing this to जो हमें given boundary condition है, given boundary conditions is the traction is just equal to f sine omega t in the one, for the one component. So it's just f sine omega t here. There is no other E2 or E3 component. So what are we getting? That this time around, our boundary condition, instead of it being on the displacement, is actually on sigma 1, 1. So अब हमें ये impose करना है. Okay, ठीक है, we can do that because हमारे पास displacement field ये रही, we can find the strain and then hence find the stress. Okay, so let's see how to do that. Now please note कि ये completely different boundary condition है, इसलिए we have to go back to this entire displacement field now, जो general wave motion की equation है. और उस general equation के ऊपर इस particular boundary condition को impose करना है. Okay, so still I hope you all can see कि u1 is just a function of x1, which means that the only strain component that's going to exist is going to be epsilon 1, 1. फिर से सिर्फ वही रह गया, फिर से, because only non-zero strain is this one. और इसी से I think we all, अब वही बात है, we just directly use this, oh no, not this one, sorry, कहाँ गया से ये, the Hooke's law, to then figure out कि sigma 1, 1 है क्या होना है. Or we, because we've already done the previous example, so I'm gonna take a few shortcuts and just jump to writing down that we know कि sigma 1, 1 in terms of epsilon 1, 1 is actually 2 mu plus lambda epsilon 1, 1. So now substituting things in here, substituting things in here, we get what? Minus f sine omega t is going to be equal to 2 mu plus lambda, or ye epsilon 1, 1. Oh, again, remember this sigma 1, 1 condition is at x1 is equals to 0, right? So this must also be at x1 is equals to 0. ये उस plane पे apply हो रही थी ना traction. So epsilon 1, 1 evaluated at x1 is equals to 0 is going to be, let's see, del u1 by del x1 तो पहले निकाले ना, ताकि epsilon 1, 1 आ जाए. This is going to be a bit complicated. ये 2 pi by L है. Okay, so that's alpha 2 pi divided by L cos of, again, this entire thing, मैं उसको ऐसे ही रहने देती हूँ, and then ये plus beta cos है, तो cos का minus sign हो जाता है, so that becomes minus beta 2 pi divided by L sine of the whole thing again. ठीक है जी, and then we're evaluating it at x1 is equal, पहले मैं ये पूरा ही लिख लेते हैं. So I have 2 pi alpha divided by L cos of x1 minus CLT minus beta 2 pi divided by L sine of x1 minus CLT. Now evaluated, as I said, at x1 is equals to 0. So what do we have? फिर वही पुरानी बात के on the left hand side there's just a sinusoidal function. So this cos term must disappear. So what does that mean? That means that this time around alpha is equals to 0. Whereas for beta, what do we have? A much more complicated one this time around. Beta turns out to be equal to f times L divided by 2 pi into 2 mu plus lambda. Don't forget there is this coefficient right here too. So ये beta आ गया compare करते हुए. And then finally comparing just the argument within the sign. What have I got? Oh, have I made a mistake? Is anybody... Is omega just equal to, is CL just equal to omega?
Ma'am, beta is equals to minus FL.
Beta is equals to minus? You sure?
Yes, minus FL over this.
Let me think. But there's a minus right here. So minus and the minus should cancel out. No?
Ma'am, there's a minus for the sign as well. Sign minus CLT.
Rabia, I'm thinking, look here. So when I differentiate it for the sine term, I have a minus now, right? So इसलिए either this minus, there's a minus here and there's a minus here. So minus f is actually equal to minus beta times all of this entire thing.
मैम वो साइन वाले के अंदर भी देखे ना, वहाँ भी एक माइनस है, वो भी बाहर नहीं आ जाएगा.
Oh, you got me. Completely right. Yes, spot on. So, as we were doing beforehand, we need to remember that the minus of the time has to also come out. Completely right. Thank you, Rabia, for pointing that out. So, when this minus comes out, so sine over minus theta is actually equal to minus sine theta. So therefore there would end up being a minus here. Thanks, Rabia, for pointing that out. Completely right. Yes. Okay. Rabia, but help me out. I am actually making another mistake as well. So I believe I have missed out. मैंने ये 2 pi L जो है मैं खा गई हूँ from within the arguments. So there are actually these 2 pi divided by L here as well. I'm sorry guys, लेकिन इतना लंबा चौड़ा वो होता है कि थोड़ी गलतियाँ हो जाती हैं उधर. So this should be also within the L. So that means that omega is actually equals to 2 pi CL divided by L. So that is then the wave velocity. No, actually I'm not. What was I interested? I was finding the wavelength. So my L actually turns out to be 2 pi CL divided by omega. This is the same as we had gotten last time. So the wavelength is still dependent on the angular frequency in the same way as it was dependent when we had a displacement boundary condition. Okay? But there's been a pretty massive change in the amplitude, beta. This one now, in the amplitude of the longitudinal wave. What's happened instead? पहले जब हमारे पास displacement boundary condition थी in part A, तो हमारे पास we had only got that alpha was equal to minus b. मतलब it was just equal to the wavelength of the causing frequency, the causing wave. Sorry. the probe की जो amplitude था. Whereas this time around, the amplitude of the wave is actually a function of this funny little thing. Material properties भी आ रही हैं उसके अंदर जो ट्रैक्शन की वेव है उसका एम्पलीट्यूड भी आ रहा है और वेवलेंथ भी आ रही है. So a bit more complicated this time around.
मैम इस दफ़ा हमने डिफरेंशिएट विद रिस्पेक्ट टू एक्स नहीं किया.
मैंने किया है, ये रहा, मतलब थोड़ा सॉरी मैं ऊपर नीचे कर रही थी, बट द पॉइंट वाज सिग्मा 1 के ऊपर हमारे पास बाउंड्री कंडीशन आ गई थी, right? So sigma 1 as we had discussed previously was just a function of epsilon 1 और epsilon 1 निकालने के लिए of course I need to differentiate the displacement with respect to x1. So I did do this differentiation और ये वो पूरा differential है इसके अंदर. Clear?
यस मैम कर रहा हूँ अभी. अगर कोई क्वेश्चन हुआ मैं पूछ लूँगा.
Sure. So now just again, as I said, just seeing the questions, they seem complicated, but they're just stretching a little bit what we have already learned. Okay? And to see them applied to a very particular boundary value problem. Okay? So just have a think about these. Do it on your own as well. I'd recommend that if you try to do it yourself, if you get stuck, do listen to this lecture again. The reason being that when you just see the solution to these sort of things, for example, if I just show you the slides, I personally don't think that will make much sense. Because slides, the thing is, वो directly चीज़ें आनी शुरू हो जाती हैं, right? वो directly वो differential आ गया. Now, how do you know what that is? So, just listen through the lecture again to if you get a bit confused. It's nothing new. It's just an application of what we have considered so far. Okay. So, yep. So this is exactly what we had just found. हमारी भी यही results आए थे. So thank you, Rabia, for pointing out the negative. As I said, this is interesting because look what's happened. We changed the type of boundary condition. Okay, instead of causing a sort of sinusoidal displacement boundary condition, instead this time around in part B we applied a sinusoidal traction boundary condition और उसकी वजह से वो wave की dynamics ही completely change हो गई हैं. And of course this is the nice thing about everything that we've done in continuum mechanics so far, because using those exact same वही तरीका वही procedure, we've just managed to figure out a completely एक बाउंड्री कंडीशन से दूसरी बाउंड्री कंडीशन में जो फिजिकल प्रॉब्लम पूरी चेंज हो गई है, हम उसको पूरी तरह सॉल्व कर सकते हैं, फाइंड कर सकते हैं, उसकी स्ट्रेस फील्ड निकाल सकते हैं, उसकी डिस्प्लेसमेंट फील्ड निकाल सकते हैं, एंड एवरीथिंग अबाउट इट. सो दैट्स एक्सट्रीमली यूजफुल फॉर अस. Okay. So right. So just as I said, I would be ending soon. This was the last example that I wanted to consider. The one more topic that I just want to, with one slide, introduce. Okay. So far, we just looked at waves in which the displacement was in the same direction as the direction of wave travel या wave propagation. मतलब ये अभी तक जो हमने देखा था अभी पीछे, you noticed कि we were looking at a displacement field of this type. U1 was a function of x1 in time. That's it. तो इसमें यही हो रहा है ना कि displacement उसी direction में हो रही है जिस direction में wave travel कर रही है. In contrast to this type of a wave, there are other waves as well which exist. So for example, something like this. where what's happening okay, you actually have a displacement in the transverse direction as wave travel, right? Here what happens, okay, the particles actually move up and down, whereas the wave is traveling in this direction, in the x1 direction. So this type of a wave is actually, because as I said, the displacement is transverse to the direction of propagation of the wave, it's known as a transverse wave. Or again, we know what another example of this kind of a wave, it is of course when we take a string और उसको एक तरफ से बांध के हम उसको ऊपर नीचे यूं हिलाएं. The wave travels in this direction, but the particles move up and down. So this string wali waves, when we propagate it with a hand, that is a transverse wave. Okay. Or again, the point is just that for us the same continuum mechanics principles hold true, of course. So अगर हमारे पास कोई इसकी problem आ जाए जी कि हमारे पास कोई boundary condition है for this particular displacement field, we are able to follow the same procedure that we just looked at in the previous example for one of these transverse waves. Same old, no issue. ठीक, हमें सिर्फ उसके ऊपर इंश्योर करना है कि the equations of motion are satisfied, the strain displacement equations are satisfied, the linear elastic isotropic stress strain law, that is Hooke's law, that is the constitutive behavior of the isotropic linear elastic solid is fulfilled. या फिर in other words just कि उसके ऊपर Navier-Lame's equation को ये fulfill करे. ठीक है जी. So इसीलिए what I'm gonna do is I'm gonna give you guys an assignment which is going to be this lies problem 5.23, which is basically just the example that we've just अभी जो हमने देखी थी just a few minutes ago, but instead it is for a transverse wave. If you notice carefully, the displacement is in the u1 direction, whereas wave propagation is in the x3 direction. ठीक है, ये भी नोट कर लें, ये वेव का जो मोशन होता है वो इस जो कंपोनेंट होता है उसकी डायरेक्शन होती है, whereas particles की displacement is given by the u's right here. So so just wanted to introduce you guys to your assignment number 5, just to get a bit more practice on using our sort of just consolidating कि हमने पूरी continuum mechanics में क्या किया है. Where I know we're using the solid mechanics as an example, but as I've said, we're using the elastodynamics as an example, but as I said, the same procedure holds true for any type of boundary value problem.